Thank you for the introduction, and I would like to thank the organizers of the conference for giving me the opportunity today to talk about this topic. So as you can guess from the title, this topic is somehow similar to what Andrei did in his presentation, but actually it's our final goal is slightly different, and we will use completely different techniques. So, okay, so this is an outline of the presentation. I will give an introduction to the problem and try to explain the motivation of why we're interested in such a problem in sub-Riemannian geometry, and then I will explain more general, slightly more general setting, and then I will give the main statement with some ideas of the proofs. Okay, so as a motivation, let's look what happens in Riemannian geometry. So we start from a complete Riemannian manifold Mg and omega, a subset of M, which for the moment we can think about to be open and relatively compact. And then we can define the heat equation, and we can study the Cauchy problem for the heat equation with the initial data given by uniform initial temperature distribution equal to 1 on the set omega, so the characteristic function of omega. Here, this operator denotes the Laplace-Beltrán operator. So we know from classical spectral theory that we have a heat semigroup, and so we can define the temperature distribution, so the solution to this problem, and then the Riemannian relative heat content will be the total amount of heat contained in the set omega at time t, where in particular this integral here is computed with respect to the Riemannian measure. Okay, so at this stage, let me just remark the fact that in literature you can also find the notion of classical heat content, where the solution U to the Cauchy problem is replaced with the solution to the Dirichlet problem. So we have, from a physical viewpoint, the boundary of omega is kept at 0 temperature for all times. So this is not the case here, and from an asymptotic perspective, these quantities are really different. So, okay. The main result regarding the relative heat content in the Riemannian setting is due to Vandenberg and Gilke, who proved in 2014 that under the assumption of M being compact and the boundary of omega of being smooth, then the Riemannian relative heat content has a complete asymptotic expansion as a function of square root of t as t goes to 0. Moreover, they were also able to compute explicitly the coefficients of this asymptotic expansion up to order 4. What is remarkable about this expansion is that, apart from the zero-order term, which is just the volume of omega, geometrical invariants of the boundary of the domain, Riemannian geometrical invariants, appear. In particular, we have as a first-order term the Riemannian perimeter measure of the boundary of omega, and as a third-order term we have some complicated expression depending on the Riemannian mean curvature of the boundary of omega, so the trace of the second fundamental form. And so we can see from this result that small-time asymptotics of the relative heat content encodes geometrical information of the boundary of the domain. And so, since in the sub-Riemannian setting we don't have a canonical way of defining a Levi-Civita connection, in particular if we consider the general rank-varying case, then looking at the relative heat content asymptotics is a way of detecting geometric information and geometrical information and geometrical invariants of the boundary of hypersurfaces in the sub-Riemannian geometry. Okay, before going to the preliminaries of my presentation, let me just remark two things about this theorem. So first of all, we have a compactness assumption. We will try to remove this compactness assumption going forward. And for what concerns the boundary of the domain, the only standing assumption here is its smoothness. This will not be enough in sub-Riemannian geometry. We will need an additional regularity assumption. On the other hand, Vandenberg and Gilke are able to get a complete asymptotic expansion. Okay, so now I will just briefly recall what sub-Riemannian manifold is. Abdelhad already introduced this notion, but here the main difference is that we allow the rank to vary, the rank of the distribution to vary with the point. So we start from a general smooth connected manifold, and then a sub-Riemannian structure will be defined by giving a so-called generating family. This is a family of n global smooth vector fields, and attached to this generating family we can define a distribution and a norm. So a distribution is the linear subspace generated by the generating family at any point of the manifold, the linear subspace of the tangent space. And we will assume that the Lie algebra generated by this distribution, so we consider the linear subspace generated by the generating family and iterated Lie brackets, is the whole tangent space at any point. This is the so-called bracket generating condition or Mander condition. And moreover, we can define, using the generating family, a norm on the distribution. So we are allowed to measure the length of vector fields tangent to the distribution. In particular, this is done as follows. So we consider V in the distribution, and its square norm will be the infimum over the Euclidean length of the controls realizing the vector V. It turns out that this norm actually satisfies a parallelogram identity, and so we get a scalar product on the distribution. And this will be our sub-Riemannian manifold. Let me remark that on the one hand, we do not require this generating family to consist of linearly independent vector fields at any point. So we are including the rank varying case, but also the equiregular case that we saw earlier. On the other hand, if we consider a generating family whose associated distribution is already the whole tangent space without considering any Lie bracket at any point of the manifold, then this procedure, this scalar product, is actually a 0-2 symmetric tensor on the tangent space, and so we have a Riemannian manifold. In this sense, we are generalizing the setting of Riemannian geometry. Then, since we want a metric space, we want to define a metric structure on this sub-Riemannian manifold, we can consider the distance, so-called sub-Riemannian distance, which is defined by Lamé minimization among admissible curves. And for admissible curves, I mean those curves for which we can measure the length, so the curves whose tangent lies in the distribution at any point. And it turns out that the bracket generating condition is enough to ensure that this distance is actually finite, continuous, and compatible with the manifold topology. Okay, so this is our setting. Now, since we are interested in the heat equation in our sub-Riemannian manifold, we need an operator replacing the classical Laplace-Beltrami operator, and this has been introduced by Abelard. Of course, I will be very quick. So we are going to define the sub-Laplacian as I did, so defining it by divergence after the gradient. The main problem in the general rank-varying sub-Riemannian manifold setting is that we do not have a canonical way of defining a measure. So if our manifold were equiregular, then we would have the pop measure, but in the general case, we don't have this kind of measure. So what we are going to do is to fix a smooth outer measure, small omega. This will always be fixed to my presentation. And then we can, of course, compute the divergence of vector fields in this way, using the Lie derivative. And we can also define the horizontal gradient, directly generalizing the Riemannian gradient by duality with the differential of a function f, but computed only on the distribution. And so finally we have this sub-Laplacian operator, which is the divergence computed with respect to small omega after the horizontal gradient. This operator has good spectral properties. In particular, it is symmetric in L2 and negative. Moreover, if the manifold M is complete, then it is also essentially self-adjoint. And so we have the heat semigroup, and we can define the solution to the Cauchy problem. And so, also in this setting, we can define the so-called sub-Riemannian relative heat content, which is the integral of U, but this time computed with respect to the measure small omega. So, as I mentioned at the beginning, the regularity assumption that Vandenberg and Gilkey had in the Riemannian case of the boundary of omega to be smooth is not enough in the sub-Riemannian setting to deduce an asymptotic expansion. And what we need in addition is that the boundary of omega shouldn't have characteristic points. So a characteristic point is defined as follows. We consider a point of the boundary of omega x, and then this is said to be characteristic if the distribution at the point x is completely contained in the tangent space to the hypersurface given by the boundary of the domain. Well, of course, we can immediately see that in the Riemannian setting this definition is trivial. Indeed, in the left-hand side we would have an n-dimensional vector space, and on the right-hand side we would have an n-1 dimensional vector space. And so this, the presence of characteristic points is a truly sub-Riemannian phenomenon. It's something that we never see in Riemannian geometry. And in some sense, we can think about this kind of points as intrinsic metric singularities of the sub-Riemannian manifold at those points. And what I mean by this is that if we consider omega to be a non-characteristic domain, so with the whose boundary has no characteristic points, then there exists a smooth tubular neighborhood of the boundary of the domain, and in this neighborhood the distance function, the signed distance function from the boundary, delta, is smooth. These results have been proved by Rizzi, Ferrari, Montefalcone in some Carnot groups of step 2 and then generalized to any sub-Riemannian manifold by Franceschi, Prandi, and Rizzi. Yeah. Okay, now before stating the main result, let me just give an example to fix the ideas. This is a very easy example of a sub-Riemannian manifold, but yet it displays some of the feature of sub-Riemannian geometry. So we start from the Lie group given by R3 together with this non-commutative product law. And we can define the two left invariant vector fields x and y as displayed. And choosing as a generating family the family given by x and y, we get a distribution which is bracket generating, and so we have a good sub-Riemannian manifold which is called the Heisenberg group. On the right hand side you can see a picture of the distribution at the plane z equals 0, and as you can see, as we follow the y-axis, the distribution tilts a bit, and this is what gives the bracket generating condition. So in this setting, since we have a group structure, a Lie group structure, we can define a canonical measure, which is the R measure, so we consider this Lebesgue measure. And then the sub-Laplacian in this case is given by the usual sum of squares of operators, and it is, of course, hyperelliptic. A remark in this setting is regards the non-characteristic assumption. So if we consider a non-characteristic domain in the Heisenberg group, due to the orientability of the Heisenberg group and using the Poincaré index theorem, one can immediately prove that its boundary must be homeomorphic to a torus. So we have a topological constraint which is a bit restrictive, but this topological constraint becomes less and less restrictive as the dimension of the manifold increases. Okay, so now to the main results. So what we proved together with Agrachev and Rizzi is the following result. So we consider a compact sub-Riemannian manifold capable with a smooth measure, and we consider omega to be a non-characteristic domain in this sub-Riemannian manifold. Then the sub-Riemannian relative content asymptotics has an asymptotic expansion up to order 4 as a function of square root of t, and we have these explicit coefficients up to order 4. So a few remarks about this statement. First of all, as I said, unfortunately we are not able to deduce the existence of a complete asymptotic expansion, differently from what happened in the Riemannian setting. However, the coefficients that we are able to compute are actually the sub-Riemannian counterpart of those coefficients that appeared in the Riemannian setting. Indeed, as a first order coefficient, we have the sub-Riemannian perimeter measure of the boundary of the domain, and as a third order coefficient, we have some complicated expression which still depends on this sub-Laplacian of the distance function, which is actually the so-called horizontal mean curvature of the boundary of the domain. So in this case, we don't need Levi-Civita connection to define the mean curvature of the boundary, but it's enough to we use this equivalent definition. Okay, so in particular, once again, we are able to detect geometrical information of the boundary of the domain omega, but in this case, we have a sub-Riemannian geometrical invariance. Okay, so before going through the proof of this main result, let me just quickly review the literature about this topic. So the relativity content was firstly studied in connection to sets of finite perimeter by De Giorgi in 1954. He was mainly concerned with giving a characterization of sets of finite perimeter in Rn. And then Ledoux in 1994 was able to actually deduce a precise asymptotic expansion for the relativity content. And in particular, they used the BV functions technique. Then this result was pushed further by Angioli, Massari and Miranda in 2013, and they proved an asymptotic expansion in the Euclidean setting up to order 3, also dealing with the boundary with low regularity. And they used an explicit expression for the heat kernel and the existence of normal coordinates. So their techniques are not really suitable to be extended in the sub-Riemannian setting. And in the Riemannian setting, the main result, I've already mentioned this, is due to Vandenberg and Gilkey, who proved the complete asymptotic expansion for the relativity content. And they used the pseudo-differential calculus techniques together with the existence of a global parametrics estimate. And this particular tool that they used is not available in sub-Riemannian geometry, and this is what prevents access to this technique in the sub-Riemannian setting. Finally, the only previous result in the sub-Riemannian setting for the sub-Riemannian relativity content is due to Garofalo and Tralli, who proved an asymptotic expansion for this quantity up to order 1, building upon a previous work of Bramanti, Miranda and Pallar of 2012, but that is true only for Carnot groups of step 2. So what is remarkable about this result is that since they were adapting techniques similar to those used by De Giorgi and Ledoux, so BV functions technique, they don't really care about the presence of characteristic points. So this is a remarkable result, but it only holds in Carnot groups of step 2, and it seems to be difficult to be generalized to more general setting. Okay, so the proof that the strategy that we adopted is actually inspired by what Savo did in the Riemannian setting for the classical heat content, and can be summed up in 3 main steps. So first of all, we have a localization principle. This localization principle is telling us that all the contributions to the asymptotic expansion of the sub-Riemannian relativity content comes from a region which is close to the boundary of the domain. So we do not really care about the behavior of the temperature function away from the boundary of the domain, but we only care about what happens in that region. But we know that if we are under the assumption of not having characteristic points, then close to the boundary of the domain we have a smooth tubular neighborhood, so we can build good coordinates. These coordinates allow us then to reduce the problem of finding the asymptotics to a one-dimensional problem. And then finally, once we have this reduction, we can exploit the Duhamel's formula and hope to get an explicit expansion. Okay, so let me be more precise about these 3 steps. So first of all, we have this localization principle, and we study this quantity, 1 minus u. Okay, so if we consider a compact set bounded away from the boundary of the domain omega, then the function y minus u is exponentially small as this goes to 0, and this behavior is uniform as long as x is in k. In particular, the proof of this result is based on 2 main ingredients. So we need stochastic completeness for the heat kernel and double-sided Gaussian bounds. In particular, these are available in the compact case. These are available in compact case thanks to Jerison and Sachet-Scala in 1986. And these 2 main ingredients in general may fail in the non-compact case, and so later I will comment about this result in the non-compact case. Okay, so now that we have this localization principle at our disposal, we want to use it to reduce our problem to a one-dimensional one. So we start from the sub-Riemannian relative content, which is the quantity here. Then we add or remove the volume of omega to let the quantity 1 minus u appear on the right-hand side. Now this quantity is amenable to localization. So we multiply in the integrand function by a function phi, which is just a cutoff equal to 1 close to the boundary and 0 in the interior. And the error and we end up with this quantity I phi of t, which is actually equal to the sub-Riemannian relative content up to this zero order term, and this error, which is exponentially small, and so it is negligible at the level of asymptotics. So now we can compute, we are interested in computing the asymptotics of this quantity, I phi of t. And the main advantage is that if we introduce a parameter r and we replace the set of integration in I phi of t omega with the upper level set of the distance function, now this function here, depending on these two parameters t and r, satisfies one-dimensional Neumann problem on the half line. Before giving you the precise statement, let me just remark the fact that if we set here r equals 0, then this reduces to the set omega, and so we end up with I phi of t. So in this sense, if we are able to compute the asymptotics of I phi of t 0, we are done. Now, as I said, if the boundary of the domain omega has no characteristic points, then the function I phi of tr satisfies a one-dimensional problem on Neumann one-dimensional problem on the half line, and we can apply the Duhamel's principle to this one-dimensional problem. Let me just remark before going on that this the non-characteristic assumption here is useful because we want to compute two derivatives in the r direction, and here the parameter r appears in this upper level set for the distance function, and so we need some regularity for the distance function to be able to compute these two derivatives. Okay, so now we apply the Duhamel formula, and what we end up is this new formula for I phi of t0. Now the problem is that this is not a precise asymptotics for I phi of t0. Notice that if we were interested in the classical content asymptotics, so if you were satisfied Dirichlet boundary condition, this would be enough because u here is computed on the boundary of the domain, and so this would be 0 for any time. But in this situation, we don't have this information, and so what we need is additional asymptotic information on the behavior of u as t goes to 0 and as x is a point of the boundary. So now this, how to address this new difficulty? Well, our idea was to look at what happens in the nilpotent approximation. So we blow up our manifold at a point x and we look at the behavior of u. What we're able to do is that under the assumption of M to be compact and boundary of, and X to be a non-characteristic point, then we are able to compute a zero-order asymptotic expansion for this function u, and in particular, so this is just the limit, and the limit as t goes to 0 of this quantity here is 1/2. So this result is rather disappointing because we would like to have a complete asymptotic expansion of this quantity, and this is once again related to the fact that we don't have a global parametrics estimate, but only a local asymptotic parametrics estimate for the hit kernel. So, okay. Now, I want to be brief about I want to give an idea of the proof of this result. So what we need is the nilpotent approximation. Now, I want to be brief about the technicalities of the nilpotent approximation. What you need to know is that the nilpotent approximation is defined as the Gromov-Hausdorff tangent to our sub-Riemannian manifold at the point x. In particular, this metric tangent exists and is unique up to isometries and can be identified with a quotient of a kernel group. And this was proved by Bellaish in 1996. So the main point is that there exists privileged coordinates thanks to which we can identify our nilpotent approximation with a special kernel group, so we can identify the base manifold with Rn, and in particular, in this base manifold, the distance function of our sub-Riemannian structure will be one homogeneous with respect to this anisotropic dilations here. So, without giving the definition of this so-called sub-Riemannian weights, what you need to think is that in the Riemannian setting, these are all equal to 1, and in the sub-Riemannian setting, this depends on the flag of the distribution. In particular, in the previous talk, we saw parabolic dilations, and in those cases, we only had 2 layers, and the first layer had weight 1, and the second layer weight 2. So this is just the generalization for a general sub-Riemannian manifold. Okay, well, now using this nilpotent approximation, we are then able to prove the result that I mentioned before. So first of all, we start by fixing a set of privileged coordinates which are adapted to the boundary of the domain omega. This means that in particular these are also tubular coordinates, and this construction can be done only if we don't have characteristic points. So immediately at the beginning this assumption still enters in the picture. Once we have these privileged coordinates, we want to express then u in these coordinates, and we can distinguish 2 main regimes of the behavior of u. So this is the regime which is close to the origin, and this is the term giving the contribution to the asymptotics. So this in the limit is 1/2. However, this quantity here should behave like a remainder term. However, due to the fact that we don't have a global parametrics estimate, we are only able to say that this is a remainder term at order 0. So this is, in particular, in order to estimate this term, we use this result by Colin-de-Vardière-Hilaire-Trellat that was mentioned also earlier, but we are not able to push this analysis to higher orders. Okay, so now, using this result about the heat flow, we are then able to deduce an asymptotic expansion up to order 1 for the sub-Riemannian relative heat content. Now, what to do for higher order asymptotics? Because since we only have this kind of formula here, and we don't have a more precise asymptotic expansion for the heat flow, we cannot really just iterate the Duhamel principle and hope to conclude. Now, the main idea here, this is a very technical proof of this, the proof of this proposition is very technical, but the main idea is that we don't really need the behavior of u pointwise. What we need at the boundary. What we need is the behavior of u integrated on the set on the boundary of omega. And so, studying this integrated quantity, we are then able to prove this proposition using a symmetry argument of the heat diffusion, introducing an outside contribution and inside contribution, and then using now this third order asymptotics for this integrated heat flow and inserting these asymptotics here, we then conclude the proof of the fourth order asymptotic expansion. And strangely enough, if one would like to push further this asymptotic expansion maybe to a fifth order, this kind of procedure breaks down, so it's not completely symmetrical. It works only up to the third order. Okay, so now before concluding, as I promised, I wanted to comment about possible extensions to non-compact case. So our main goal, our main final goal was to include in our analysis, for example, kernel groups, which are non-compact. And so, as I said, the two main problems are given by the stochastic completeness and the double-sided Gaussian bounds. And in particular, the localization principle may fail. So what we did was to look for general assumptions under which we could recover these statements. And so we look at our sub-Riemannian manifold as a metric measure space. And now we assume that as a metric measure space, M is globally doubling and supports a weak global Poincare inequality. Then one can prove that actually M is stochastically complete and the it kernel enjoys this double-sided Gaussian bounds. Finally, using the previous result, one can actually prove the same theorem that we had before, removing the compactness assumption, but by following exactly the same strategy. Now, to conclude, let me just mention that Carnot groups now are included in this class of sub-Riemannian manifolds, satisfying that are globally doubling and supporting a global Poincare inequality. In particular, the measure in this case is the R measure. And another class of examples of sub-Riemannian manifolds satisfying these assumptions is given by Rn equipped with the Lebesgue measure and a distribution generated by a generating family of vector fields where the vector fields have bounded coefficients together with all the derivatives. Okay, this concludes my presentation. Thank you for the attention.